Hello, Miss Barber here. Now that you know how to count using counting techniques, in this lesson you will learn how to compute probabilities that may require the fundamental counting principle, permutations, and/or combinations. To compute such probabilities, you will need to first determine which, if any, counting technique to employ, and then proceed. Example: Leonard, Penny, Sheldon, Howard, and Raj have all been invited to Amy's dinner party. They arrive randomly, and each person arrives at a different time. What is the probability that Howard will arrive first and Penny will arrive last? This is a counting principle problem, and we've got 5 positions to fill. The 2 that are specific is who arrives first, that's for Howard, and who arrives last, that's Penny. Now we look in this basket and we see images of these characters. If Howard is to arrive first, there's only 1 of him and 5 in the basket, so the probability that he arrives first will be 1/5. Continuing. Now that he is no longer in the pool, there's only 4 left to remain, and the next 3 who arrive, the only criteria is that they are not Penny. So there's 3 characters out of 4 who are not Penny. If one of Raj, Howard, or Sheldon arrives, then there's 2 characters remaining of the 3 who are not Penny, so the probability is 2/3. And now there are 2 characters remaining for which 1 is not Penny, which means there is a 1/2 probability that the one that is not Penny will arrive. All that's remaining now is Penny. And so for the last position, there is a 100% chance that the arrival is going to be Penny. Continuing, we multiply across, and the probability is 6/120, and we could reduce that to 1/20. Example: 3 people are randomly selected, 1 person at a time, from 5 freshmen, 2 sophomores, and 4 juniors. Find the probability that the first 2 people selected are freshmen and the third is a junior. To solve such problems, I like to have a basket and then put in tickets representing each member of the set. There are 5 freshmen, so I'll put in 5 tickets, each with F on them. There are 2 sophomores, so I will put in 2 tickets, each with S on them to represent sophomores, and there are 4 juniors, so similarly I will put in 4 tickets, each with J on them to represent juniors. Now we need to determine the number in our sample space, and that would be 5 freshmen plus 2 sophomores plus 4 juniors. The sum is 11. This is a counting principle problem. We've got 3 positions to fill. The first is a freshman, the second position is freshman, and the last position, it needs to be a junior. From this basket, we have 5 freshmen out of 11 total students, so the probability of getting a freshman for the first position is 5 out of 11. Now that one of those freshmen has been selected, there's only 4 freshmen left, and there are only 10 students left in the basket. So the probability of selecting a freshman from the revised sample set will be 4 out of 10. We selected another freshman. Now there's only 9 students left. We want to select a junior. There's 4 of them, so that probability will be 4/9. Multiply across, your probability is 80/990, and this can be simplified to 8/99. Example. Suppose that of the 25 prospective jurors for a trial, 8 favor the death penalty and 17 do not. If 12 jurors are chosen at random from these 25, what is the probability that exactly 4 jurors will favor the death penalty? This is a multi-step problem. We'll work them out. I'll begin with, in how many ways can 4 jurors be selected who favor the death penalty? Let's note, the statement of the problem says 8 favor the death penalty, and of the 8, we want any 4. That's a combination problem, so the number of ways here would be 8C4. Now, let's determine in how many ways 8 jurors who oppose the death penalty can be selected. The problem tells us there are 17 who oppose the death penalty. We want any 8 of those. Order doesn't matter. That again is a combination, so the count will be 17 choose 8. Now that's to pick 12 specific ones. We need the sample space. That is, in how many ways can 12 jurors be selected from a group of 25? This again is a combination problem, and so from the group of 25, we're going to choose 12. Now, let's put this together. In how many ways can 12 jurors be selected in which 4 favor death penalty and 8 do not? That takes us to a counting principle problem. We want those who favor multiplied to those who oppose, and we computed these combinations previously. Those who favor, that was 8 choose 4, and those who oppose, it was 17 choose 8. Now we're ready to construct the probability. The formula is the number in your event divided by the number in your sample space. Our event is 12 jurors, of which 4 favor the death penalty and 8 do not. So, for the numerator, we will have what we just obtained, 8 choose 4 times 17 choose 8, and then we will divide by any 12 that we select from 25, so it'll be 25 choose 12. Now use your calculator to compute. 8 choose 4 is 70, and then 17 choose 8 is 24,310. Use your calculator to compute 25 choose 12. It turns out to be 5,200,300. Let's do some arithmetic, and when you do, this reduces to 143 divided by 437. Example. A small combination lock on a suitcase has 3 wheels, each labeled with 10 digits from 0 to 9. If an opening combination is a particular sequence of 3 digits with no repeats, what is the probability of a person guessing the correct combination on the first try? So we want the probability, which is given by the formula, the number of elements in your event divided by the number of elements in your sample space. Our event is one correct sequence of the 3 digits. We don't want more than one correct sequence of digits. Our sample space is 3 different numbers, and the order is important. Thus, this is a permutation. So the number in our sample space will be computed as a permutation. We're going to pick 3 from 10. That would be 10 permute 3. Now we can go back up and compute the probability. N of E is 1. There's only one correct combination, and we'll divide by 10 permute 3. Use your calculator. The 1 in the numerator stays the same. 10 permute 3, using your calculator, is 720. So the probability is 1 in 720. You can also give a decimal approximation, which would be roughly 0.0013888889. You can express this as 0.14%. Example: a park board consists of 6 women and 4 men. If a committee of 3 people is to be randomly selected, find the probability of selecting 1 woman and 2 men. We begin this recognizing that we need to use the counting principle, and that is, we need to figure out the number of ways in which women can be selected and multiply that to the number of ways in which men can be selected. Both of these processes require combination. The problem says pick one of any of the 6 women available. So that's a combination. We can write that as 6 choose 1. And pick 2 of any of the 4 men available. So it would be a combination as well. 4 choose 2. Now we got to determine the sample space. That's our denominator number. 6 women and 4 men is 10, and from that we need to choose 3. So let's get ready to do our probability, which is the number of elements in your event divided by the number of elements in your sample space. In our event, it's 6 choose 1 times 4 choose 2. And we will divide that by the 10 people on the board. We want any 3, so that's a combination. 10 choose 3. We'll use our calculator to compute. 6 choose 1 is just 6. And we'll multiply that to 4 choose 2, which is also 6. And we'll divide that by 10 choose 3. That's 120. Multiplying across and reducing, the final probability in simplified fraction form is 3/10. Example: an experiment consists of dealing 5 cards from a standard 52-card deck. For this problem, the order in which the cards are dealt does not matter. Part A. What is the probability of being dealt 5 black cards? We want the probability. The formula for that is N of E. E is the event, divided by N of S. S is the sample space. Our event is 5 black cards. There are 26 black cards in a deck. Any 5 will do, so this will be a combination. 26 choose 5. We divide that by any 5-card hand from the deck of 52. This is also a combination, but this time it is 52 choose 5. Using your calculator, let's compute the events combination. 26 choose 5 is 65,780, and we'll divide that by the number of 5-card hands possible. That's 52 choose 5. Using your calculator, you should get 2,598,960. That's approximately 0.025310124. You can express this in percentage form as 2.53%. What is the probability of being dealt 4 black cards and 1 red card. For this event, we're going to use the counting principle, and we're going to need to find the combination of getting 4 black cards and multiplying that to getting 1 red card. You still have 26 black cards in a deck, and you want any 4. Order doesn't matter, so that's a combination. 26, choose 4. For the red, you have 26 red cards, and any red card will do. So that's still a combination. We would write 26, choose 1. To compute our probability, again, n of E divided by n of S. For our numerator, it's going to be the product of 26, choose 4 times 26, choose 1, and that's going to be divided by the total number of 5 card hands possible. That's 52, choose 5. Use your calculator to compute each of these combinations. 26, choose 4 is 14,950. We want to multiply that to 26, choose 1, which is just 26. And we'll divide that by the total number of 5 card hands possible, which would be 2,598,960. The product of the two terms in the numerator is 388,700, and we'll divide that by the 2,598,960. This is approximately 0.149559824. You can express that in percentage form as well, and that would be 14.96%. Example: if you are dealt a 5-card hand from a standard 52-card deck, what is the probability that you were dealt a full house? A full house consists of 3 cards of one kind and 2 cards of a different kind. For example, AAA 22, 555 KK, and 33399 would each be called a full house. We're going to begin this problem by first computing the probability of one specific full house, say 777 KK. This requires us to use the counting principle. We need to find or determine the number of ways to get 3 of a kind, and in this instance, 3 sevens, followed by 2 of a kind, or 2 kings. Well, there are 4 sevens in a standard deck of cards, and we want 3, any 3 of those, so that's a combination. 4, choose 3. There are 4 kings in any standard deck of cards, and we want 2, any 2, so that's a combination. 4, choose 2. How do we compute the probability? Well, that's the number of ways in which you can get the event you want divided by the number in the sample space. So, for the n of E, we're going to have 4, choose 3 times 4, choose 2, and that will be divided by the number of 5 card hands possible, which would be 52, choose 5. That's the probability of getting, say, 777 KK. Now we're going to extend this to any full house. So let's recollect what we've already discovered. With the counting principle, that is a way to get one full house. However, you can get a 3 of a kind by having 3 aces, 3 twos, 3 threes, 3 fours, 3 fives, and so on, all the way to 3 jacks, 3 kings, 3 queens. That is, you have 13 possible different ways to get a 3 of a kind. Now, if you do get a 3 of a kind, In order to get a 2 of a kind, it cannot be of the same number or type for which you got the 3 of a kind, so only 12 are left to choose from. So you got 13 different to choose for the 3 of a kind, and then 12 because you have one less. The product of 13 times 12 is also 13 permute 2. So for the probability in which we need n of e divided by n of s, we already had the 4 choose 3 times 4 choose 2 divided by 52 choose 5. What we have to do is now extend that to any full house, so we will multiply that by 13 permute 2.